In the voltage follower circuit, I took a look at the first of the two equivalent definitions of what an op-amp does. The one that said an op-amp will do whatever it takes with the output voltage in order to make the voltage at these two inputs the same value, and you hook the output voltage back up to one of the input voltages. Now, that led to the voltage follower circuit. But take a look at this next, very basic op-amp circuit. I've got things hooked up a little bit differently here. Now, I have the non-inverting input hooked straight to ground. Now, as soon as I do that, the first thing that I ask people, ground is at 0 volts. And so the voltage here is 0 volts. And that's right there at the non-inverting input. It's hooked into ground. Now think about the physical consequences of this. And I'm going to do this in terms of taking my function generator, and I'm going to put a plus or minus 100 millivolts or 1/10 of a volt signal into this. So I have my nice little sine wave. And I'm doing this so that I put it across this resistor and I'm driving current through this resistor. Now you know the current goes first one way and then the other, but I'm just going to look at the current going this way first. So there goes the current, boom, through the resistor. So it goes from here at, say, a positive 100 millivolts down to, now again, the op-amps do whatever it takes to make sure that that voltage is the same as that voltage. So that means that this right here is also 0 volts. And you say, great, then what? Well, the current would like to go into the op-amp because, if the current goes from high to low, then maybe the current says, I'm going to go to ground, and the op-amp goes, no. The op-amp will do whatever it takes to not let any current into that input. No how, no way. And it does this by adjusting the output voltage. So think about what's got to happen. You've got to take the current that's trying to go into the inverting input, and you've got to drag it around that way. So when this thing happens to be at positive 0.1 volts, this is at 0 volts, to drag the current all the way around here and to get there. And that current is going to be pulled, if necessary, into the op-amp right here. That's what it will do. The voltage here at the output will be adjusted to drag that current around. And the only way you can do that is to pull that current around there. Think about what's going to happen. You're going to have a voltage drop across this resistor. And so if this is positive 0.1 volts, and this is 0 volts, and you've got to drag the current down here, then that output voltage had better be, first of all, a negative value. Because the only way you're going to drag the current down from 0 volts is to have a negative voltage down here. The second thing, you've got, the way that I've got it drawn here, a 20 times larger resistor here to drag the current through than you've got here. So whatever the voltage here is, it better not only be negative, but it better be 20 times the magnitude of what's sitting here driving that original current down. So that better be minus 2 volts. If I'm at plus 0.1 volt, this is 0 volts, I have to put this at minus 2 volts, whatever it is. Now again, that voltage here is going to do something crazy like drag the current in here if necessary. And again, remember, all the internal circuitry in the op-amp does is whatever it takes to drag whatever resources it needs from the power supply to make this happen. So the stuff inside here, I don't care how it works for now. All you have to know is that this output will do whatever it takes to make this voltage happen. So if this thing over here happened to be something like minus 0.1 volts, then that means the current would be coming this way. And so this thing, in order to send the current around the op-amp and to get down here, the current's coming that way. It can't come out of here. It had to have come around this way. So the output voltage would have to be the negative sign of this one because you got to go through 0 volts. So the V out would have to be a minus voltage over here. I'm sorry, a positive voltage over there. And it would have to be 20 times larger to shove the same current through a 20 times larger resistor. So positive 2.0 volts. So not only have you amplified the voltage at the output from the input, but you've also inverted it. This is called an inverting amplifier. Because not only does it amplify the voltage, it inverts it, and it gives it a negative sign. It flips a sine wave into a 180 degree flipped sine wave. But the other thing is, let me show you this. I want to make sure that you understand this. Now again, whatever current goes through this resistor here must also go through there. Ohm's law. The current that goes through the first resistor here must be equal to the current that's going through the second resistor there. Ohm's law. Ohm's law is delta V over R. So the difference in voltage across this thing, you can't say Vn. That's wrong. It's Vn minus 0 volts. So Vn minus 0 volts divided by R1. The voltage across here, you cannot say V out. You've got to say 0 volts minus V out. Delta V, 0 volts minus V out. That minus is important because now that you've got this written out, those zeros and that minus sign come into play. But look what happens. You have a situation where your output voltage is amplified by the ratio of those two resistors. Conceptually it was okay, but mathematically it works out. It's amplified in magnitude by those two resistors, and this negative sign inverts it. So it's an inverting amplifier sitting over here. But also, take a look again. You have your input current over here, your output current over here, driven by this voltage, but look at the power over here. If you go off and you calculate the input power over here, you're going to have 0.1 volt difference squared divided by 1,000 ohms, and that is going to be 10 to the minus 5 watts. All right, so look at your output over here. If I do the same kind of power calculation on the output, then I am going to have a maximum of 2 volts, 2.0 volts quantity squared divided by 470 ohms. So that's going to be 4 divided by 470, which is, and that's watts, which is in general vicinity of a milliwatt. It's less than a milliwatt. And so, I'm sorry, it's less than 10 milliwatts. So by the time you punch this up, you have also amplified the current, because this voltage has to be maintained across a smaller resistor, but the op-amp will do whatever it takes by putting out whatever current is required to make this happen. So this basic inverting amplifier allows you to amplify the voltage. The negative sign will come into play, but it amplifies not only the voltage, but also the current. The previous one, the voltage follower, simply amplified the current. So these operational amplifiers can do all sorts of great and glorious things.